Now, previously, we have talked about differential equations, and we've talked about separable equations. I want to now look at a specific kind of equation and see how that differential equation comes up in a lot of practical problems. So, we're going to talk about growth and decay problems. And let me highlight what the key concept is here. We'll first just look at growth, and then tomorrow we'll look at decay problems and link the two together. So I'll write out a sentence. So quite often, what scientists have found through experimentation and investigation, if we're looking to describe the growth of some population, it could be bacteria, it could be people, it could be anything in between. So over time, the population grows, the quantity of whatever you're measuring grows, and you'll have, let's suppose, the number of individuals, number of bacteria, number of people, whatever it may be. And if you track that over time, what people have found is the rate, let's say the growth rate, let me write it like this. The population grows at a rate proportional, that's an O, proportional to the population size at that time. So what does that mean? That means that if your population is over here at some point in time, then the rate at which it grows, the rate of change, which I know is the derivative, the slope of the tangent line, is related to how many individuals there are at that time. Then I grow a little more. Let's suppose I grow to that point. Then the rate of change is proportional, is connected directly to how many individuals there are. And therefore, because there are more now, they grow faster because there's more interactions and more opportunity for population growth. So let's define a function. Let's say big N, which is a function of time. Let that represent the population size at time t. Now it depends on the situation. It depends on the situation. If sometimes time is measured in seconds, sometimes time is measured in days, months, years, it doesn't matter. I would know beforehand what exactly the time unit is. N represents how many individuals there are, how much of the quantity, whatever I'm representing or measuring. Then the growth rate. The growth rate is, of course, dn dt, the time derivative. Now, when these two things are proportional, it means the ratio of the two is a constant. Or in another way, maybe a simpler equation, proportional means that one is related to the other by just a constant modifier a constant factor. So this is going to be our key differential equation to describe how the population changes. Its rate of change is some scaled up or down version of the actual population. So that if the population size goes up, then they grow faster, and vice versa. I also, of course, need to know, let me just clear my box here. I also need to know how many there were at the start. And let's call that N0. So I would need to know, not always, but usually, the initial population size. Let's just make that a specific constant. I could start with 100 individuals. I could start with 10,000 bacteria. It depends on the situation. So here we have our basic population growth initial value problem, differential equation with an initial value, so I can actually find a particular solution. So before we go to any practical problems, I need to understand how to solve this differential equation and how the initial value comes into my eventual function, because this kind of equation is going to come up over and over and over. So I'm going to solve this in general first to see what it looks like. Now we'll redo that over and over and over for each question to practice, but let's do it in general first. So solving this differential equation. So it's going to always be the same. My function is now an n, and my independent variable is a t. Remember, k is a constant. It's called the growth constant. And it'll change in value from one situation to the next. The growth constant for bacteria won't be the same as the growth constant for people, and so on and so on. So I'm going to separate my variables because the n is on the wrong side. So I'm going to bring just the n to the other side. And remember, I leave my little differential separation until the end. Then I can multiply both sides by dt to get this, and I integrate both sides. Same as before, we're just going to look at this specific equation that comes up a lot in growth and decay problems. Now the right-hand side is pretty straightforward. Because k is a constant, it's just going to be k times t. I put my constant, my integration constant there before I forget it, just so it's out of the way, but it's really a grouping of all the constants that come out from these two separate integrals. Then on the left, I look at that in isolation. So n is my variable for this antiderivative question. 1 over n's antiderivative is natural log. Now I'm not worried about absolute values or any technicalities here because we know that our population is always going to be a positive number. Now, this would be a perfectly fine general solution under normal circumstances, but I have a practical problems in mind, and so it would be beneficial for me to solve for n so that I can have a function that I can use to answer follow-up questions. So I now have a reason to simplify this and make it look a little nicer by solving for n. And in this case, just based on our understanding of log equations and their link to exponential equations, I can very easily write this as n equals e to the kt plus c. So it's important So it's very important to understand what these constants are. K is my growth constant, a part of the original problem, and C is my integration constant that comes out of the solving of the differential equation. So I need to use my initial condition to find the value of C. So we still need to find C. But before I do that, it turns out that I can make this look a little nicer to have this integration constant be connected to something that has immediate meaning. This C, if I calculate the value of this C, it doesn't really, its value isn't obvious where it comes from. But if I rewrite this a little bit, it's going to look much nicer. So what we're going to do is we're going to write this as e to the c times e to the kt. Now if c is a constant, that would mean that e to the c is also a constant. So whether I try and find a value for c or e to the c, it doesn't really matter as long as I find one of them. So I'm going to call it, just so it's a little bit nicer, let's call it M or something. Doesn't matter. Some books I've seen use an M, so let's use an M. So now M is just another version of my integration constant. This is still an integration constant, but soon it's going to be a much nicer version. So now I'm going to use the fact that at time 0, I have an initial population n0. So that is what goes in place of my population size, and time is 0. So I put that in place of time. Now e to the 0 is just 1, so that means that my integration constant is the initial population size. And so my function that describes the population is the initial population times e to the kt. So having the integration constant in front here gives it direct meaning that I can easily pick out from the word problem as the initial population size. So it's just a nicer constant to see in my function. So there is my population growth model's answer, and this is why they call it exponential growth, because it's an exponential function. I'm going to start with some initial population size, and then it's going to grow exponentially, having some growth factor here, growth constant k, adjusting the curve a little bit, but regardless, it is an exponential function. So it's very important that in every word problem, we are able to set up I'll do it like that. They were able to set up the differential equation for that problem with perhaps a specific k value, perhaps a specific initial population, depends on what they're giving me, show how I solve it, but it's always going to be very similar, you'll see, then get the function, and then use that function in whatever question they may want. So let's look at specific questions. And we'll see that there's a lot of similarity between these. Let's look at this first one, growth of bacteria, 14.3. Consider the population of bacteria that grows at a rate proportional to the population size. So that tells me that's the differential equation we're working with. The growth rate is proportional to the population size with a growth constant of 0.02. So they give me the growth constant. Initially, there are 200 bacteria. They give me the initial bacteria amount. How many bacteria are present in the population after 5 hours? When does the population reach 100,000 bacteria? But before I can answer those questions, I need to set up the differential equation, which is a translation of this first sentence. So let's do that first. So let's say n, which is a function of time, represent the number of bacteria at time t. Then the sentence, this first part of the sentence, grows at a rate proportional to the population size with a growth constant 0.02 is translated to my differential equation as dn dt equals 0.02 times n. And initial population, they also tell me, is 200. So this differential equation translates the information in words. Now, before I continue and I have to use the function that comes from this equation as a solution to answer follow-up questions. So my next goal is to show how this differential equation leads to the function that I can use. So I do it for practice, but the procedure is always the same for a similar looking differential equation. So I separate the variables in the exact same way. Then I integrate both sides. So the natural log of n is 0.02t plus my constant, and therefore n is e to the 0.02t plus my constant, which I'm going to write as big M e to the 0.02t, with m being e to the c, exactly the same as before. So then I'm using the fact that my initial condition is 200, plug that in, so 200 equals m times e to the 0.02 times 0, and that, because e to the 0 is 1, leads me to m being 200, which I already knew should be the case. So my function that describes the number of bacteria over time is 200 e to the 0.02 t. Now, we know what this function should look like because we've done it in general, and it comes from the same looking equation. But a first part of the question could say, set up the differential equation and show why this is the function. So I have to practice this solving of the differential equation step as well. However, now that I have the function, I simply need to use that function to answer their questions. And their first question is, how many bacteria are present in the population after 5 hours, 300 minutes? Now, they didn't say these questions, it's a first draft of this book. They didn't quite say exactly what the time unit is. In this case, I'll just clarify that the time unit, I believe, is in minutes. So let's just go up here. But a test question should definitely clarify that. So now after 300 minutes, we have n of 300. And so we plug that in. So our basic question, we have a couple of basic questions. Whoops. First one is, I have my function here. Given a time value, what's the population? So 300, I plug in, I calculate that. Let's see what that is. We get 80,685.76, let's say. And the other question is, given a target population size, when does that happen? So I still use my function. So if I get a target of n equaling 100,000, then I simply plug in 100,000 for n and solve for t. So e to the 0.02t equals 100,000 over 200, which you can leave like that, or you can simplify it. In this case, it's going to be 500. So that means that 0.02t equals natural log of 500, only 100. 500. So t equals log of 500 over 0.02. Let's calculate that. Now I have to check what MathBot does for my log function. I'm guessing it's just ln. Let me just test it first. Yeah, okay. And we get 310.73. So we have 100,000 bacteria after approximately 311 minutes, or we can keep them decimal. 310.73 minutes. So the point here is we have a question that's answered really in two parts always. The first part is translating the key information about how the population grows And for our purposes, it's always going to be at a rate proportional to the population size. That translates to a differential equation. We then show how to solve that differential equation, simply to practice, just to be ready if that is in fact the question. And after we solve the differential equation, and therefore get a function, we can use that function to answer follow-up questions. Now 14.4 here I do want to do, but this is not the complete question. It comes up later. So let us just see another variation of this with 14.6. And it's now just a matter of practicing to see all the little variations that could come up. This is still a word problem, so if they don't define the variables for me, I'm going to have to do that. They do define t, and t is standard for time. But in general, I have to define my variable if I am going to use anything that, if I'm going to use anything that they didn't define, I'm going to have to define my variable at the very start, which is usually the population size function. I don't have to call it n, I can call it something else. Let's call it y in this case. Let y, which is going to be a function of time, represent the population size, the number of bacteria, at time t. Now let's see their words here. Under ideal laboratory conditions, the rate of growth of bacteria in a culture is proportional to the size of the culture at that time. I have that proportionality property, and that allows me to say that the rate of change of the population size is some constant times the population size. And initially, I might have an amount. Let's see. So in this case, they tell me 2,000 bacteria are present initially, but they don't tell me the growth constant. So I'm going to leave that as a k. Sorry, how much? 2,000. 2,000 initially. And k is going to be my, right now, unknown growth constant. We have to figure it out soon, but we don't know right now. Before I can even worry about their questions about 5,000 are present an hour later, how many bacteria will be in the culture at the end of 2 hours, I have no idea. I would need the function to answer any of those questions. So the first part is always going to be, how do I solve the differential equation to get my function, or at least show how that is done, to then continue with the rest of the question. And the nice thing is that that's always the same. So I separate the variables rather, and k is unknown in this case for a while. I integrate, I get the natural log equals kt plus my integration constant. So y is e to the kt plus my integration constant, which I rewrite as m times e to the kt, with m being e to the c. I'm doing this on purpose every time because the first part of the test question might ask me to verify how to solve this differential equation, even though I know the target we're aiming for. Then I use the fact that the initial population is 2,000, plug that in. So it's really just a formality that I can memorize to a large degree. I get m equal to times e to the k times 0. Regardless, that's a 1. So m is equal to 2,000. Big surprise, I knew it was the initial population. And so my function is 2,000 e to the kt. Now, this isn't quite complete. I don't quite know what the growth constant is. So next I'm going to have to find the growth constant. Find the growth constant k to be able to really know the function. And that is why they give me the information that there are 5,000 bacteria present 1 hour later. So just to mix it up, let's go with t in hours this time. And as long as I'm consistent, it really doesn't matter for this question. But working with a 1 is so much nicer. So what do we know? That y at 1 hour is 5,000. I can use that, plug it into my function to get a value for k. So e to the k is 5,000 over 2,000, or 2.5 if you want to simplify it now. So k is natural log of 2.5. Let's calculate that. Whoopsie. I get k as 0.9163, let's say. Now, in a future calculation, I do have to use the accurate k, but when I present it, I can certainly round it to 2 or 4 decimals. I'd like 4 if they don't specify anything, just for that extra little safety, but it's up to you because it's just a presentation. Now we can finally get to the question. How many bacteria will be in the culture at the end of 2 hours? So now we can find the y value when time is 2 hours. Quite straightforward. I'm going to keep the k as a k, even though I am aware I do have the number if I need to. I don't want to write a messy decimal number in there. But when I use k in a calculation, which I'm going to do now, I do use its accurate value. So I would say 2,000, whoopsie, hold on, 2,000 times e to the power of 2 times log 2.5. And we get 12,500. This is a word problem, so a concluding sentence is a very nice idea. Let me just check the question here. How many bacteria will be in the culture at the end of 2 hours? At the end of 2 hours, there will be 12,500 bacteria. Sorry, my zeros are a little flat sometimes. And there we go. Let's zoom out. I'll zoom out some more. So there's my question. Just to prepare for any variation in a test question, I start by translating the information into a differential equation over here. I then show how the differential equation is solved to get to the answer, which is my function. In this case, I didn't know the function completely, so a little more was required, which they do give me information for. Then I have my function, and I can answer the final part and conclude with a concluding sentence. All right, so that is a typical population growth question. Let's just try and cover some variety by looking at one more. And then you can totally practice all the questions up to 14.4. Tomorrow we will look at radioactive decay. All right, 14.5 as our last question for today. Assume a population of fish grows at a rate proportional to the population size. Key sentence again. A pond is stocked initially with 500 fish. After 6 months, there are 1,000 fish in the pond. The owner will allow his friends and neighbors to fish on his pond after the fish population reaches 10,000. When will the owner's friends be allowed to fish? So before I worry about any of that, I define my population function variable and set up the differential equation, which is a translation of this first sentence. Let's do that. Let's go with a y again. Let y represent the number of fish, the population size, at time t, and in this case, time is in months. Then, the fact that they tell me the population of fish grows at a rate proportional to the population size, that allows me to translate the sentence into a differential equation. K is my growth constant, and again, I don't know it right now, but that's not a big deal. Initial population, initial number of fish, 500. So I have most of it. Then, just to practice and prepare, I show how this differential equation leads to my exponential growth function. Then 1 over y dy is equal to k dt when I separate the variables. I integrate both sides. I get natural log of y equals kt plus a constant, the integration constant. Y is equal to e to the kt plus c. And this is always going to be the same. Sometimes I have k, sometimes I don't. Sometimes I have initial population, sometimes I don't. Who knows? Then I'm going to write this as big M, e to the kt, where big M is equivalent to e to the c for convenience. So I then use the fact that my initial population is 500, plug it in, 500 for y, 0 for t, to get m equal to 500. And big surprise, my function is the initial population times e to the kt. I still need to find k to be able to use this function completely, but they also give me extra information they give me the fact that after 6 months, there will be 1,000 fish. So this is what we call doubling time, that from 500 double to 1,000 takes 6 months. And we'll say something about that in a second. Right now, I don't really care what information they give me. I just need information to get this growth constant K. So in this case, the information is the fact that after 6 months, I have 1,000 fish. Let's use that. Plug in 1,000 for Y. Plug in 6 for T. And E to the 6K equals 1,000 over 500, or in this case 2. So 6K equals natural log of 2, and K equals natural log of 2 over 6. Let's see what that is. We get 0.1155 and some change. So now we have our function completely. Even though I write K, I am aware that I have an exact value for K. It's just an ugly decimal number. I don't want to put it into my function. So now let's see what their question is. Now, the owner will allow his friends and neighbors to fish in his pond after the fish population reaches 10,000. When is that going to happen? So I have a target population size. I want to know when that happens, 10,000. So my target population size is 10,000. I use my function. Let's just peek at what K is at the same time. So that means Y of some T value is 10,000. So 10,000 for Y equals, what's my function? Over there, 500 e to the kt, and I know what k is whenever I need it. So e to the kt is 10,000 over 500, which you can simplify if you want to. Some zeros cancel out. I get 20. So kt is natural log of 20. So t is what I'm trying to solve, log 20 over k, which I do have. Now you can put in all the decimals, or you can calculate it as log 2 over 6, but don't use a rounded number in a future calculation. Let's do it. So different ways you could set that up. We get 25.9316, if you will. So now T was in months. So it's going to take a while for his neighbors to come fish. It's going to take almost 26 months. Now I look back at my question. When will the owner's friends be allowed to fish? So the friends will be allowed to fish after approximately 26 months. Now, I can be aggressive in my rounding in my concluding sentence, because it's a nice and presentable number. It's close to 26, and I do show the exact number. So I satisfy both camps, just having a nice sentence with a nice number and the exact answer coming from my calculation as well. So in our last 3 minutes, I want to just notice something more about this doubling time, but I need more space. So let's just say a little more about this doubling time. That'll help me tomorrow as well. So let's call it tau. So what it's going to be is it's going to be the time when that it takes for the population to double. So initially, we have the population size is, let's say here, 500. 500. Then it doubled to 1,000 after time tau. In this case, it was 6 months, but it might not be, right? If we want to find that population, that doubling time, this means that, how should we say it, that y of this doubling time period is 2 times 500. Now, I'm not married to the 500. It could be anything. Let's change it. If I make that y0, any initial population size, then I have to change these guys as well. It doubled to, not erase it, 2 times y0. 2 times y0. So I can then simplify the left-hand side because I know the function. The function is my exponential growth function, y0 e to the kt. So now for this specific time value that I'll just call tau, something else, to remind myself it's a specific time value, I have y0 e to the k times tau equal to 2 times y0. Now solving for tau in this equation, it shows that I divide both sides by y0, so e to the k tau is 2 times y0 over y0, and the actual y0 value didn't matter. It didn't matter if it was 500 or 10,000 or anything. I just get a 2. So k times tau is natural log of 2. So my doubling time is natural log of 2 over k. This is completely independent of how much I started with, of my initial population size. It's a property of the population and how it grows. So if I were to graph this out quickly, I have my population size, my exponential growth here. Whatever I start with, it's going to take a certain length of time, tau, to double to twice what it was. It's going to take the exact same length of time to double what it was previously, so 4 times. It's going to take the exact length of time, which I can't see here, to double what it was. Every time period of tau, 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 the population doubles every time, and it grows faster and faster and faster. Now, this doubling time concept becomes a little bit more important when I talk about radioactive decay, which we will do tomorrow. All right, that is it for today. Practice some population growth questions, and we'll see a variation with decay problems tomorrow. All right, are there any questions at this stage? All right, then we will continue this discussion tomorrow. Thank you.